Good afternoon, everybody. This video is in response to Jay's question, which I didn't get into in class, and I'm really glad I did because it definitely the specific problem we're looking at is it would be getting into derivative stuff we're going to do in quite a bit, a couple of weeks out into the future, and let me explain. So the original question Rebecca brought to class, and it had two moments that were not neither continuous nor differentiable. And one of them is kind of real and one of them is kind of fabricated. And what I mean by that is what you're looking at right now. Actually, let me look at I started with this on screen so anyone who's in class today can remember exactly what we're looking at, where we have this asymptote at -1 and we also have this hole at +1. So the easy answer to that question is just where a graph is not continuous, it's not differentiable. So the answer to this question was this is not differentiable at -1 and +1, but for different reasons. So I'm going to change this, and notice if I click on this other thing, it goes right on top. So I'm going to sort of unclick the original and just say to match the equation that we brought up in class would be -1 over x plus 1 squared plus 2, which is basically from the toolkit function 1 over x squared. This is flipped over the x-axis and it's shifted up into the left. But on this graph, basically, you'll notice that -1 is the only problem. If x equals -1, we get a 0 in the denominator, and we get the results of this vertical asymptote at -1. The second one I graphed, this one in red, which again matches with it directly. All I did was multiply top and bottom of that fraction by x minus 1, basically creating a problem at x equals +1 that's removable in that if this is factored, you can see that x minus 1 cancels out. However, it still matters that the original function on this has an x minus 1 in the denominator. So the x being +1 creates a problem. So as I started to get prepared to explain this to you, this was a little complicated of a problem, and it was going to make it tougher. So I created a bit of a simpler graph so we won't get into the weeds too much. So I just said, let's look at the graph of 1 over x, which is this graph right here. We're very familiar with it. It's a hyperbola with a vertical asymptote at x equals 0, a horizontal asymptote at y equals 0. And then do the same thing by sort of fabricating a problem by saying, let's call this x minus 1 over x times x minus 1. In other words, we just multiplied top and bottom of the equation by x minus 1. So it actually gave us the exact same thing. But if you do this thing where you sort of investigate at 1, you'll notice this is always so finicky. Yeah, it keeps popping up. Yeah, at x equals 1, it's undefined, right? And Desmos doesn't even show you that because it's this removable discontinuity. So I'm going to switch over. And ultimately, I'm going to show you the math. This is 3.3 stuff that gets into the rules. So it's a little bit of a preview of 3.3. And let me switch my share to this Word document. If we look at the first function of 1 over x, and remember, the only real problem is at x equals 0. There's no problem at x equals 1. Let me just switch to draw tool. So another way you could think of this as we could just call this x to the power of -1. And again, I'm going to assume you've read 3.3. The power rule really says whatever power is there, turn that into a multiplier and then drop this power by 1. So this becomes the derivative of this is f prime of x equals -1 times x to the -2, which we could also write as -1 over x squared. As you can see, x equals 0 is both a problem for the original function, f of x, and also for its derivative, because x being 0 puts a 0 in the denominator in both cases. So now let's look at the second one. Second f of x, which graphs is the same thing with just this added removable discontinuity of x equals 1. So this gets a little more complicated. And I'm going to have to give you another differentiation rule that we haven't talked about yet. And that's one way you can look at this is you can think of this as two, I probably should have, let's call this h of x actually, because so we don't confuse f of x with this. If you look at this as f of x divided by g of x, in other words, define f of x as x minus 1, define g of x as x squared minus x. Let's also just say, all right, well, if f of x is x minus 1, f prime of x in this case would just be x to the first power just literally becomes 1, as in x to the first power, you multiply the 1, the first power, well, let's kind of show you. X to the first power, turn that 1 into a multiplication and go from x to the first power to x to the 0th power. So that's really x to the 0th power, which is just 1 times 1, which is 1. So the derivative of the numerator is 1. The derivative of the denominator is x squared becomes 2 times x. The squared goes from the second power to the first power. And then just like we saw here, the derivative of x itself is just 1. So this becomes 2x minus 1. And again, if you haven't done 3.3, you haven't seen this explanation, so it's probably a little much. And then the rule for this is the derivative of some function f of x, g of x. Let's say the derivative of h of x is the derivative, oh, if we break h of x into f of x over g of x, the derivative of h of x is going to be the derivative of f times g, not the derivative of g, minus the derivative of g times f, not the derivative of f itself, all over g of x squared. And I know this is a lot all at once, but this is introduced later. So I wish there was more space. What's this going to let me do? Let me just, maybe by zooming in, I can do this. Just create some space here. And remember, we already just found, I'm not even going to do this whole thing. I'm not going to spend the time on that. All this to say, if you look at this function, all this stuff on the top works out just fine. It would be, polynomials multiplying. But on the bottom of this, g of x squared, that's all that really matters. I'm just going to say, let me switch to a different color. G of x, which is x squared minus x. It means the denominator of this derivative is going to be x squared minus x squared, which we could also call x times x minus 1 squared. And all this is to point out that in the derivative, x is 0 would create a 0 in the denominator, and x equals 1 would also create a 0 in denominator. So all this to say is if those both create zeros in the denominators in the original function, they're also both going to create zeros in the derivative in the denominator of the derivative. So it's also, the derivative is also undefined at those moments as well. Jay, this is for you. I hope that helped. If it confused you all, it might be just because the question came up earlier than we really had the tools to do a proper job breaking it down. And we can return to it later if you need. Thanks, everybody. I will see you next time.